Welcome to week 4 of Finance 301. This week we are going to look at Chapter 7, the time value of money. We are beginning our discussion in Part 2 of our text, which covers Chapters 7, 8, and 9. Chapter 7 is crucial to financial decision making. Helps us answer such questions as, if I invest $3,000 a year for 30 years and earn 5% annually, how much will I have in my account at the end of that 30 years? Or, if I buy a home and take out a $200,000 mortgage at 4% for 30 years, what will be my periodic payments? Or, if my company buys equipment for $100,000 and it generates cash flow of $31,500 for 5 years, what will be the return on investment? It is important that you take the material covered in chapter 7, 8, and 9 very seriously. A strong background and understanding of the time value, risk measurement, and analysis of financial statements will make comprehending the remainder of the topics a lot easier. I want to go over a few housekeeping items. First and foremost, our discussion board posts and the points that are assigned to those. As a reminder, in order to receive full credit, you must make an initial post and then respond to at least 2 of your classmates' posts. Failure to do so will result in not receiving the full 10 points each week. Here is a breakdown of receiving your maximum points. Your initial post is worth a maximum of 6 points, and then your 2 required responses are worth at least 2 points each. So if you make your initial post and then respond to at least 2 of your classmates, then you can receive the full 10 points. However, if you make your post and respond to only 1 of your classmates' posts, the maximum amount of points you can receive is 8. If you only make your post and do not respond to any of your classmates' posts, the maximum points you can receive is 6. So be sure to do all 3 requirements so you're receiving your maximum points each week. Also, 2 weeks from now, your topic report is due by Sunday, September the 15th by 11:55 p.m. With the number of students that is in this class, it is imperative that you have those submitted to me by the due date so I can grade them and get them back to you in a timely manner. The future value of a dollar. The time value of money allows us to relate amounts at different times so that the real world decisions can be made. A dollar to be received in the future is worth less than a dollar received today. Future value of a dollar is the amount to which a single payment will grow at some rate of interest. Appreciation is also called compounding. And so what you've got to realize is that as we move forward in the future, there is a term that we've talked about called inflation. Things cost more in the future than they do today. Therefore, in the future, the value of $1 is less than what that value of the dollar is today. I've heard several people talk about this, and especially my grandparents and their generation would talk about how they used to be able to go to the store and with a quarter be able to buy a soda, a bag of chips, and a candy bar and still receive change. And that is kind of mind-boggling to us because today a quarter can buy very little. Especially not a soda, candy bar, and a bag of chips. And so what we have to understand is that as we progress forward, the value of a dollar decreases. Therefore, that's why it's so important that we make wise investments and we take money today and invest for future returns in hopes that those future returns are greater than the inflation that is occurring naturally as we move forward. Compounding It is a process by which interest is paid on interest that was previously earned. The longer the funds compound and the higher the rate at which they compound, the greater the future value. So, if you take $100 and you invest it in the bank today, in a year, if you earn 5%, that $100 would be worth $105. If you leave it in the bank and allow it to draw interest again for another year, then that's where compounding comes in, because now your money is not only, or the money is not only drawing interest on the initial $100, but it's also drawing interest on that $5 of interest that it earned. So now it's drawing interest on $105, and then again the following year, and again the following year. As long as you leave that money in there and allow it to draw interest on top of interest, that's what we refer to as compounding. The future value equation is P times 1 plus I to the nth power equals P to the future value. So it's literally, the breakdown of that is present value times interest factor equals future value. And P is the present value, the amount or principal. I is the rate of interest, N is the number of time periods, and then interest factor is FVIF, or 1 plus I to the nth power. This shows the future value of $1 at 10%, and then also at 5%. And you can see there that the curve is not just a straight line, it's an upward curve. And the reason for that is where it goes into compounding at different intervals and the various interest rates that it can incur. Because interest rate will play a huge role on what the future value of money is based on the interest rate that you receive over time. Future value example. The future value of $100 at 5% at the end of 20 years would be written as 100 times 1 plus 0.05 to the 20th power equals P to the 20, which is the future value in 20 years. So that would be 100 times FVIF, parentheses 51, 20N, or 100 times 2.653, which means in 20 years that $100 investment would be worth $265.30. The time value problems can be illustrated with timelines, and so at 0 you invest that initial $100, then at the 20 years it would be worth the $265.30. And so each year it's going to gain interest and compound each year to where that's how you're making your money. And because if at the end of the year you take out the interest earned each period, then you're not earning interest on interest, which means you're going to end up earning less money. Financial calculators have 5 special keys: N, I, or percentage, which is your interest, present value, your payment, and future value, where N equals the number of time periods, I equals interest rate per period, PV is present value, PMT is annual payment, and future value is FV. To express the cash outputs as cash inflows and outflows. So at least one of the cash variables must be an inflow, which is represented by a positive number, and an outflow, which is represented by a negative number. For example, if you put in present value equals negative 100, interest is 5, N is 20, payment is 0, the future value would come out to be $265.33. The present value of $1. So the opposite of compounding is discounting, which determines the present value of funds that are to be received in the future. The present value of a future sum depends both on how far in the future the funds are to be received and on the discount rate. And it is set up similar, except that you're going to be dividing instead of multiplying. So it's the future value over interest factor equals present value, where P is the present value or the amount or principal, I is the rate of interest, N is the number of time periods, and the interest factor again is 1 over 1 plus I to the nth power. And if you remember in our previous figure, the present value of $1 to be received in the future is a downward curve, as opposed to the upward curve we've seen when you're looking at the future value of money. If the interest rate is 6%, the present value of $100 to be received 5 years from today would be, so you would take the $100 that you're going to receive in 5 years, it would be over 1 plus 0.06 to the 5th power. When you do the math on that, it would be worth $74.73. So if someone said in 5 years from today, I'm going to give you $100, that $100 in the future for the present value would only be worth $74.73 today. So let's practice. If the interest rate is 8%, what is the present value of $100 to be received 3 years from today? I want to give you just a few moments to get that set up. So if the interest rate is 8%, what is the present value of $100 to be received 3 years from today? So you would take the 100, put it over top of 1 plus 0.08 to the 3rd power, and so that would be worth $79.38. An annuity is a series of equal annual payments. The future value of an annuity is the amount to which a series of equal payments will grow at some rate of interest. And so there's an ordinary annuity, which are when payments are made at the end of each time period. For example, under an ordinary annuity, you would make a payment, say, at the end of the month or at the end of the year. Whereas in an annuity due, payments are made at the beginning of the time period. For example, you would oftentimes this is kind of like if you get a lease to rent an apartment. The owner of the apartment will typically want the first month's rent up front, and then you have to pay at the beginning of each month. And so that's an annuity due. And so you make the payment at the beginning of the time period, month, year, etc. The future value of annuity equations. The future value of an annuity due, FVAD, equals payment times 1 plus interest rate to the 1st power to the 2nd power on in to the nth power. The future value of an ordinary annuity, FVOA, is very similar, except that, again, remember, at an ordinary annuity, you're making the payment at the end of the month. So that first payment is to the 0 power. and then you start moving forward because, again, it's at the end of the month instead of at the beginning of the month. PMT is the equal periodic payment, I is the rate of interest, and N represents the number of years that elapse from the present until the end of the period. Future value of annuity due, payment times FVAIF, parentheses IN, where payment, again, is the equal periodic payment. FVAIF, parentheses I comma N, is the interest factor for the future value of annuity at I% and N time periods, and FVA is the future value of the annuity. You can also do those on timelines. And again, I want you to notice that annuity due, at 0, there's $100. Why? Because you have to put that first payment up front. Whereas an ordinary annuity, at year 0, there's no payment. And then at the end of the first periodic payment, whether it be a month or a year, that's where that $100 would show up there. So let's look at what that means. So on the top here we have a flow of an ordinary annuity. So initially the amount in the account at the end of the period, 0 initially because again you paid at the end of each pay period. So then at the end of the first pay period you would have 100, then at the end of the second 205, and then at the end of the third 315.25. Whereas if you compare that to the annuity due, and again, that's where you deposit or make that payment up front. So you begin with $100, and then at the end of the year, it's worth $105. Then at the end of the second payment, it's worth $215.25. At the end of the third, $315, or at the beginning of the third, it's $315.25, and then the interest at the end, you have $331.01. So again, you can see as with an annuity due, you're going to make more money than in an ordinary annuity simply because that $100 is up front and then begins compounding. You can see here in figure 7.3 the future sum or value of an annuity of $1 over the course of a 15-year time period based at an 8% or in a 4% growth. If the interest factor for the future value of an ordinary annuity at 5% for 3 years is 3.152, the interest factor for an annuity due for 3 years at 5% is 3.152 times 1 plus 0.05, which is 3.3096. If this interest is applied to the example of $100 deposited in the bank at 5% for 3 years with the deposit starting immediately, the future value would be $330.96. The present value of an annuity of $1. The present value of an annuity is the current value of a series of equal payments to be received in the future. PV of an annuity equation. Annual annuity payment is multiplied by an interest factor to determine the present value of an ordinary annuity, where PMT is the annuity payment, PVAIF parentheses I comma N is the interest factor for the present value of an ordinary annuity of $1 at I% for N time periods, and PV is the present value of the annuity. And so again, you can see the present value of an annuity of $1, the curvature there as it goes forward at both 4% and 8%. The interest factor for the present value of an ordinary annuity of $1 for 3 years at 6% is 2.673. Interest factor can be converted into the interest factor for the present value of annuity of $1 for 3 years at 6%. So 2.673 times 1 plus 0.06 would be 2.833. Thus, the present value of an annuity due of $100 for 3 years at 6% would be 100 times 2.833, which is equal to $283.30. An employer offers to start a pension plan like a 401k for a 45-year-old employee. The plan is to place $1,000 at the end of each year in an account that earns 6% annually. The employee wants to know how much will be in the account by retirement at the age of 65. So the present value equals 0. Payment is $21,000. I is 6%, N is 20, and so the future value would be worth $36,785.59. So we get the 21,000 because you put the $1,000 in, and it's going to earn 6% annually. And so by the time he retires at the age of 65, that money would be worth $36,785.59. Example 2. The same employer decides to place a lump sum in an account that earns 6% and to draw on the account to make the annual payments of $1,000. After 20 years, all the funds in the account will be depleted. How much must be deposited initially into the account? So again, FV is 0, payment is 1,000, interest is 6%, N is 20, and so the present value we would need $11,469.92 to be deposited initially into the account. Example 3, you buy a stock for $10. You expect its price to increase 9% annually. After 10 years, you plan to sell the stock. What is your future anticipated sales price? So this question illustrates the future value of $1. So the present value is 10 because you're buying that stock up front, so it's a negative 10. Interest is 9%. It's for 10 years, and then the payment is 0 because you're not going to be adding anything to it, but the future value would then be $23.67. So your $10 investment then becomes worth $23.67 over the period of 10 years if it grows at 9% annually and you don't add anything to that. Example 4. You sell a stock for $23.67 that was held for 10 years. You earned a return of 9% per year. What was the original cost of the stock? This is an example of the present value of $1 discounted back at 9% per year for 10 years. So your future value is $23.67. Your interest is 9. Your N is 10 for the number of years. You're not doing a payment, so you're not adding anything to it. So your present value would be negative 10. Example 5. You bought a stock for $10, held it for 10 years, then sold it for $23.67. What was the rate of the return on the investment? So your present value is negative 10. The number of periods is 10. Payment is $10. The future value is $23.37, and then you would be able to get your interest of 9%. An investment pays $50 per year for 10 years, after which $1,000 is returned to the investor. If you can earn 6%, how much is this investment worth? This question really contains two questions. What is the present value of an annuity of $50 per year for 10 years at 6%? Plus, what is the present value of $1,000 to be received 10 years in the future when discounted at 6% per year? So the present value, when you put all of that in, if you put it into a financing calculator, the present value would be $926.40. You purchase a home for $100,000. You make a down payment of $20,000 and borrow the balance of $80,000. The mortgage loan is for 25 years and the rate of interest is 8%. What is the annual payment required by this loan? Mortgage payments are usually made monthly, but in order to keep this illustration simple, just assume that the payment is made annually. So your present value is $80,000. Interest rate is 8% for 25 years. Your payment per year would be $7,494.30. You can see here on Exhibit 7.2, this is selections from a loan amortization schedule for an $80,000 mortgage at 8% for 25 years. Annual payment, again, $7,494.15. Your net payment one, interest payment, $6,400. Principal payment is $1,094.15, and that leaves you with a loan balance of $78,905.85. So notice, initially you are paying more interest than what you're paying towards the principal. But as you go forward, you begin to close the gap, and your principal payment begins to be greater than your interest payment, which is what begins to reduce the balance of the loan. So by year 25, the balance of the loan would be zero. Example 8. Your 85-year-old Auntie B has to enter a nursing home that charges $8,000 per month, or $96,000 a year. You have power of attorney and sell her home for $470,000. Excluding any other sources of income such as Social Security payments and any other expenses, for example doctors, how long will her money last if you are able to earn 8% annually? So the present value would be $470,000 at 8%, future value 0. The payment is $96,000, and the N, which is how long it's going to last, it would last approximately 6.46 years. Non-annual compounding. Compounding can and often does occur more frequently, such as twice a year or semi-annually or monthly. No annual compounding is payment of interest more frequently than once a year. Non-annual compounding is payment of interest more frequently than once a year. Periods of less than 1 year. Suppose a cash manager invests $98,543 that will return $100,000 at the end of 45 days. What is the annual rate of the return? So N is 45 days, or 45 over 365, which comes out to be 0.1233 of a year. So your present value is the negative $98,543. N is 0.1233. Payment equals 0 because we're not doing any more payments. Future value is $100,000. So the interest earned, or the annual rate of the return, would be 12.64%. Non-annual compounding with a financial calculator. All variables must be based on the same unit of time. For example, number of months, a monthly interest rate, and a monthly payment amount. The interest rate is understood to be a percentage. Divide the annual interest rate by the number of periods in a year and not have to do any math to account for the non-annual compounding. It will account for the compounding on its own. Compute the monthly payment of a $20,000 loan that is borrowed today, paid in full, that is, the future value of the loan is zero when it is paid off and the balance is zero, after 5 years of monthly payments and has a 6% annual interest compounded monthly. So the present value is $20,000, interest is 6, future value is 0, N, or the number of payments, is 5. The payment would be $4,747.93. Divided by 12 would be $395.66 per month. How can the concept of time value money be applied to your everyday life? And again, it goes back to the examples. If you were to place $1,000 in your retirement account each year for the next 30 years, how much would you ultimately accumulate? Or you're purchasing a home or a townhome, need to borrow $250,000. What are your payments going to be? Or say that within 5 years you want to save up $100,000 to start a business restoring cars. How much must you save annually to achieve your dream? All of these can be answered by studying and knowing this chapter. I encourage to make sure that you watch the additional videos that I have shown. It shows some more examples, walks you through some things on the topics covered in Chapter 7. Be sure that you respond to the discussion post and make your initial post and then respond to 2 of your classmates. And also, if you have any questions, need anything, please feel free to reach out to me via email. I hope that you have a blessed and wonderful week. Thank you.